so you're reading in chapter 8. Continue reading in chapter 8. 8.68, I believe, is an excessively long section because it's all the different functional groups. There's lots of pictures. But it's all the different functional groups and the types of fragmentation. But work your way through that. And then I'll get your homework for this week posted today. The other thing on the agenda today is the discussion of written report 2. I'm also going to be discussing the group project that you're going to do at the end of this semester. So it's kind of a joint thing. Those of you that are in the writing will do an additional portion that you have to do a written report in addition to the presentation that you give in class. So I'll go over that towards the end of class. Let's get started. A little bit about mass spectrometry. Hopefully this slide is nothing new. So what is it we're looking at in mass spectrometry? First up, we know that we can determine the molecular weight of our molecule that we're analyzing, also known as an analyte. So you can determine a molecular weight, and then from there we can do rule of 13 or something like that to figure out possible molecular formulas. And we find that molecular weight when we're looking at our M plus peak. The molecular formula can be determined if you're using high-res mass spec, which we don't do too often. We don't have that capability here. But in common research settings, they're going to be sending samples out for high-res mass spec, which analyzes the sample to 3 or 4 decimal places, and you can get enough significant figures to actually determine the exact molecular formula. And that's the HR's high-res solution mass spectrometry. You can get some information about the structure based on fragmentation patterns. So we're going to go into a lot of detail on fragmentation patterns on Wednesday and how we find them in the mass spectrum and how the molecule is breaking apart. And they're going to be in consistent patterns that we're looking for. You can look at the different isotopes, and that can lead you to tell you things about what types of atoms are incorporated into the sample. So if you have chlorine, we know, or bromine, those affect the isotopic distribution of our M plus peak, and we can look at that. We can also associate those with the fragmentation patterns to know approximately where in the structure those are. So you can look not only at the M plus and the M plus 2 peak to look for bromine, but if you see that same type of pattern in other places in the spectrum, you know that fragment contains bromine as well. And so that can give you a little bit more information about where it might be located in the structure. Finally, if you're in biochemistry, you could use it for protein sequence, and we'll talk about some additional techniques that are required for mass spectrometry of proteins. Typically, we've talked about small molecule analysis, and when you're talking about something that's 1,000 or 10,000 AMUs, or molecular weight, it gets a lot more complicated and different. The protein sequence typically is done using what's called MS-MS. So you take a mass spectrum of the sample as it's going through, and then you have another fragmentation pattern, or event, and then you take a second mass spec. So you're going to ionize the sample, you're going to take a mass spectrum, and then you further fragment and ionize again, and those break apart, and you get more information from the second mass spec. And it's all in line, it's all done at one time, you don't do it in separate chunks. Well, yeah, not separate experiments, I should say. So those are the basic things we're going to be looking at. Now let's look at a basic setup for a mass spectrometer. So this is the thing from your book, and you'll see that you have your initial sample. So then initially the sample needs to be introduced somehow, and that's going to be the sample inlet. We'll talk about a few different types in the next few slides. So this is our introduction, ways that that can be done. Then we need to form ions, because mass spectrometry measures masses of ions, not molecules, so we need some type of ionization to occur. That's going to be on our ion source. We're going to have then a mass analyzer. So the mass analyzer somehow has to separate out all the different masses of the different ions. So if you have an ion that has a mass of 10, you need to separate it out from the mass of 20 in order to differentiate them when we actually go to the detector. So the mass analyzer is going to separate the ions. And that's based on the mass to charge ratio. So you separate them out based on their mass to charge ratio, and then they go to the detector, and that quantifies the ions. Notice that we need to be under high vacuum. We are going to be looking at single ionized molecules. And so we need this in a gas phase. In order to do that, we need it for most samples to be under high vacuum, and sometimes unique ways of getting them into the gas phase in order to get them into the mass analyzer and the detector. But everything needs to be under high vacuum in order to keep them from condensing back into a liquid or solid phase. It's always nice to see a visualization of some of these things. So we'll watch the first part of this. They go over basics of the instrument and show you on a specific instrument how it works.
This instrument is called a magnetic sector instrument. The sample is introduced here, and the positive ions are formed here by bombardment of the sample with a beam of electrons. The ions are then accelerated by an electric field and then deflected in a curve by a further electric field. They then bend through a magnetic field and are further deflected by another electric field here. The ions then enter a detector here. By varying the electric and magnetic fields, ions of different mass can be made to enter the detector. These pumps keep the interior of the instrument under a high vacuum. This is to allow the ions, which are moving at speeds of many kilometers per second, a free path without collisions with air molecules. As the ions are formed from molecules of the sample, they may fall apart or fragment. The ion of largest mass is here. We're running samples are placed in the tiny sample tube. Liquid samples are placed in the tiny sample tube as shown. Here we're running the mass spectrum of limonene, an alkene which can be obtained from the peel of citrus fruits. Only a little is required. Mass spectrometry can detect down to as few as 10 to the minus 12 moles. Volatile samples can be run neat. Less volatile ones are dissolved in a solvent such as dichloromethane, which then evaporates. The sample tube is placed in this probe, which is then inserted into the instrument via an airlock, so that the vacuum in the instrument is maintained. Volatile samples will vaporize at the low pressure inside the instrument, but the probe can be heated to vaporize less volatile ones. The electrons stream out from a heated cathode towards an anode, which is held at a potential of around plus 70 volts relative to the cathode. This is the ionization chamber where the positive ions are formed. These are formed when high-energy electrons strike the sample molecules. You can think of this as the electron beam knocking out an electron from the sample molecule. The sample fits here, and ions pass out through this slit. The heater itself is here. The electrons are accelerating in this direction, and the ions stream in this direction through the slit. The positive ion beam passes between two charged curved plates, which deflect it in a curve so that it enters the area here, where an electromagnet produces a vertical magnetic field. This further deflects the beam in an arc of a circle. On emerging from the magnetic field, the beam is deflected again by another set of charged plates, which direct it into the detector. The amount of deflection...
I'll come back to that. But that's your general setup. You saw an example of the introduction of the sample, and then the ionization, and then different methods of separating up the mass to charge. This is the magnetic sector one. We'll talk about different ones, and I'll show you the rest, or another part of this when we come to that. First, we want to talk about the sample introduction. So they had one technique that they were using there. There we go. Okay. So that would be sort of like the direct insertion probe, where it's being directly inserted into the mass spec instrument, and you're able to get the sample from that. There's a few different ways. The key here is that somehow your analyte must be in a vapor phase. And so we need some way of inducing them to come into a vapor phase. First set here is the batch or the reservoir. This is only really useful for things that are already gases. So if you have a sample that you want to measure, say the content of ozone in the atmosphere, or different organic contaminants in your air sample. You could take a sample of that air and connect it, and then that is connected to the mass spectrometer. The vacuum inside the mass spectrometer is going to start pulling some of the gas into it, and then go through the ionization, separation, and detection. It also works for very volatile liquids. So these are kind of your small molecules that you can't use it's only useful for those. The direct insertion probe is also useful for very low vapor pressure solids and liquids. This can happen with a lot of smaller organic molecules, and this one, like they had directly inserting the sample. Sometimes you just have a wire loop that you put the sample on, and that gets injected into it. And for this one, it's going to heat the loop or the probe after it gets into the source, and then you can vaporize your samples, and they can go into the ionization. And these two in particular, you would want to use only on very pure samples. If you were trying to identify just one molecule, you would want to have a very pure sample so that that's the only ions you're seeing in your mass. You wouldn't want to use those for mixtures of things. So the batch and the direct insertion probe, you primarily would want to use with very pure samples. The membrane sample could be used for an aqueous solution or some type of air samples. And this, you're going to have a membrane that certain things can pass through and other things would be left behind. So it's a diffusion-based separation. The last one is probably the the one we have here, and this is where you have some type of chromatography that happens before it gets to the mass spectrum. So we have a GC mass spec, or gas chromatic mass spectrometer, and we can separate out mixtures of things based on their volatility, and then once it gets to the end of the gas chromatograph, it's going to be introduced into the mass spectrum. And you can also do that with an LC, or a liquid chromatography mass spectrometer. Unfortunately, we only had a UV vis detector on our liquid or HPLC, I should say, high performance liquid chromatography. But we would love to have one that had the mass spec on it as well. Difference between those two: for gas chromatography, again, you need things that are going to be volatile enough to actually move into a gas phase and be separated in that way. And the limits on most of our columns is about 250 degrees Celsius, which is pretty high, but there are certain limits on what we can get to come through on that. The LC, anything that you can get to dissolve into a liquid mobile phase is going to be easy. You can separate out. So it's a little bit more useful in that, and more versatile. The key here, though, is that you are going, for each of these first few, the sample can be there and it can keep throwing ions out into the mass spectrometer, and it can take a long time to detect everything if it wants to. For gas chromatography and liquid chromatography, you've got a narrow space of time where that ion or molecule is going to come through, in which you can detect it and actually quantify it. And so it needs to be a very fast mass spectrometer that can keep detecting things as they're coming through. So each of these kind of have their advantages and disadvantages. We'll go over one more, which would be a matrix, where you actually put your sample into a matrix, and that's going to be associated with one of our ionization techniques. So we'll go into that in a little bit more detail. Questions? So after we get the sample into the mass spectrometer, it's in a gas phase, we need to ionize it. The one we talked about before is the electron impact ionization, and this uses the electron beam. We'll go into it in more detail on the next slide. This is the most common ionization technique. So most people, if they're doing small molecule, they're going to be using electron impact. This is limited to relatively low molecular weight compounds. Here I'm talking about 600 AMEFL. So for most of the stuff we're talking about in this class, for your small molecule organic things, this is very good. If you're talking about something like a protein or a biomolecule that's going to get up there in molecular weight, it's not so useful, and that's why we'll use some of the other techniques. Chemical ionization is the next one we'll talk about. It's ionization using a chemical instead of an electron beam. This is one that gives very little fragmentation, which can be useful in some ways and not so useful in other ways. And that also is useful for our low molecular weight, not MS, molecular weight compounds. So something less than about 800 AMUs. The last two are more useful for our larger molecular weight. So the first one is the desorption ionization. So this is good for higher molecular weight or things that are very labile. And labile means, in this case, they're somehow reactive. So either thermally they would be reactive, or if you're hitting them with an electron beam, they're just flying apart and you're not able to see anything. And so very reactive compounds may need the desorption ionization. The last one is the electrospray ionization, not to be confused with the electron ionization. So we have EI for electron ionization. Electrospray ionization would be ESI. In electrospray ionization, again, we're looking at our larger molecular weight compounds. Particularly, it's used for the LC mass spec in biomolecules. For the LC mass spec, I said that can be useful because anything that can dissolve in a solvent, you might be able to analyze. The problem is that then you have your sample dissolved in a solvent, and you have to get rid of it. The electrospray will give us a way to get rid of it, so we can actually analyze those as individual ions. So we're going to go through each of these individually on the next few slides. First one is the electron ionization. In the electron ionization, we're going to be hitting the sample with an electron beam. You saw that in the video that I showed already. They had the electrons going parallel to the sample coming through, so your sample has to come through this beam of electrons, and when the molecules get hit by an electron, it will bounce off. So the first electron is going to just bounce off, and it's going to excite another electron so much that it's going to be ejected from the molecule. So you end up with a net of losing one electron from your molecule. So in particular, we're looking at an electron beam here. The first electron just kind of hits it and bounces off. But it transfers some of its energy to another electron of the system, and that gets ejected out. And that causes us to have a positive ion, but it's also a radical. So this is what we call our radical cation. So we've lost one electron, which makes it a radical, and because it's lost that one electron, you have an overall net plus charge. Typically, this electron beam, as I mentioned, is at 70 electron volts, which is actually significantly higher than the amount of energy it would take to ionize an atom, but we want to make sure that we're getting lots and lots of energy so that we can ionize lots of them and get different ions that you can analyze. This is considered a hard ionization. As you can imagine, you're giving the atom or the molecule a lot of energy, and that energy is going to then be dispersed by getting rid of an electron, but they still are pretty high in energy, and that's what causes the different fragmentation patterns. So they're trying to get to a lower energy state by breaking off pieces and just dissipating that energy in different ways. So we do see fragmentation because this is a hard ionization. So there are several advantages, and there are also several disadvantages to this technique. The advantages here, it's inexpensive. As long as you can generate an electron beam to ionize, it works pretty well. It's versatile. And reproducible. All of this means that it's relatively easy to do electron impact or ionization. Another advantage is that you get fragmentation. And there are databases available where if you run the mass spectrum of a sample and you can compare it to a library or a database of other mass spectra, and it will do relative comparisons and try and tell you whether you have the same type of molecule or not. And there are a few databases, the NIST and National Institute of Standards and Technology has a mass spec database, which we actually have up on our GC mass spec. So if you were to look at one of your peaks and you could match it with some other things. Problem with that is if they don't have that particular one in there, they're not going to find a match for you. So it's some benefit, but not necessarily going to tell you exactly what you have. Disadvantages. Well, fragmentation. In particular, are you going to see your molecular mass? With very sensitive molecules that can't take a lot of energy, then they just fragment completely when you give them an electron beam, then you're not going to see your molecular mass peak, so it makes determination of what you have a little bit more complicated. So fragmentation is both a plus and a minus. Yeah.
Saying that it's reproducible, is that mean that the other ionization ones aren't reproducible? I get confused on, like, you get the same results every time.
Right.
You do it.
For electron impact, it's very easy to reproduce. You have the electron beam that's set at this parameter, as long as all the other parameters are set, it's fairly easy to reproduce. Some of the later ones, particularly the desorption ionization, can be a little bit more complicated, and the electrospray.
Oh, so there's more variables that can change.
Yeah.
Okay.
The other disadvantage is that you must have a volatile sample. So we need something with a low molecular weight. And that pairs with our direct insertion probe and with the batch or the membrane, possibly, but not necessarily with some of the other techniques. So this is the most common, it's the one that we use on our mass spectrometer, and it does give you a lot of information. But that fragmentation can in particular be a problem if you're looking for your molecular ion, especially if you're trying to get a high-res mass spec. You have to have the molecular ion in order to get a high-res mass spec. And so chemical ionization is a technique that is used to try to get the the molecular ion peak. Chemical ionization uses a pre-ionized reagent gas. So you have a reagent gas such as methane, ammonia, isobutane, hydrogen, methanol. Something like that is going to be our ionization reagent gas. On the slides that you may have printed out, I had methane, and methane at the beginning and the end is actually methanol. How is this going to work? We're going to take, let's look at ammonia. So with ammonia, this is going to be hit with the electron beam. So essentially using the same idea that we used for the ionization of our actual sample, now we're going to ionize ammonia. Then ammonia is going to get excited, lose an electron, and you get 2 electrons out. And you get the radical cation of ammonia. That radical cation is going to encounter another molecule of ammonia, or it can, and it can yank away one of those hydrogens and form ammonium plus a radical. NH2. This ammonium is now the ionized reagent gas. That pre-ionized reagent gas is what is going to then be shot through the sample of our molecules coming through, and the molecule that we're analyzing, our M, is going to react with the ammonium. Now, instead of electrons being transferred, we're going to look at protons being transferred. And so we're going to see M plus H plus, where our molecule has taken a hydrogen and we get NH3 ammonia out. It takes a lot less energy for a molecule to accept a hydrogen than it does to get bombarded by an electron and kick out another electron. So we would call this a soft ionization. And that typically leads to less fragmentation.
Why did you say it was soft again?
Because it's not quite as vicious. That's the word I can think of right now. You're transferring a hydrogen, which we learn in Gen Chem and organic. It's not that difficult of a process to transfer a hydrogen between molecules, especially if you match up the acid-base properties. So we're transferring just that one hydrogen to form an ion rather than electrons. The key here, though, is that your M plus peak is no longer M plus, but it's M plus 1 plus, because you've added a hydrogen. And that's likely going to be your most abundant ion in your sample. There are, as I show here, several different reagents that you can use, so methane, ammonia, isobutane, hydrogen, methanol. They each have slightly different energies that they would be transferring the hydrogen with, and so you may have to match the reagent that you're using to the molecule you're getting to get it to first ionize at a good amount and not ionize and then fragment too much if it's getting too much energy again. That type of thing you would leave to an experimental. I can't expect you to try and identify what's going to be the best reagent gas for any individual molecule that you're trying to analyze. But just know that essentially any of these, the methane, the ammonia, they're going to be accepting the electron, ionizing, and forming some type of pre-ionized reagent gas. So what are the advantages and disadvantages here? Again, it's inexpensive. It's selective. So you can have selectivity if you have a sample that may contain two things. You may be able to selectively choose a chemical ionization reagent that would ionize one of them better than the other, and you're going to get that sample. And so you have the ability to tune for the different molecule you're looking for. Based on what reagent gas you use, you're going to have a large M plus H plus peak, and that's going to be your molecular ion. So where the electron impact or ionization technique doesn't necessarily show a molecular ion, chemical ionization almost always does. So that can be a benefit here. And negative ions are possible. This requires different reagent gases. But if you have a functional group that easily ionizes to lose a hydrogen, you may see a M minus H peak that would be a minus charge. So you could analyze in a negative mode and look for negative ions and detect those as well. Disadvantages, no fragmentation. So the fragmentation is lessened so you can actually see the molecular ion, but if you don't have the fragmentation, you're not necessarily going to know the different structural features that we can determine from the parts of the molecule we can see in the electron ionization technique. Questions about that? Alright, let's look at the desorption ionization. So in desorption ionization, you have a matrix that contains some of your sample. And the matrix needs to be tuned specifically for the type of desorption ionization that you're doing. Your book goes into a lot of detail on all of those, so I'm not going to spend a lot of time on the different matrices that are used. But essentially, for your best matrix, you want it to be non-volatile. You want it to be inert as much as possible, and some type of electrolyte. So you don't want your matrix to be too volatile or it's going to end up in your mass spectrum, and that is a drawback of several of these methods. So you see a lot of whatever the matrix is made out of rather than your actual sample. You want it to not react with your sample, but it needs to be some type of electrolyte that can be transferring the charges to your sample. So what's going to happen is you're going to somehow have a beam. So if we're looking at the SIMS, we're going to use cesium. I feel like I'm saying the wrong one. Let's take a look over here.
55.
Bottom left. There we go, it is cesium. Okay. So you have an ion that you are bombarding the matrix with. That causes ionization of the sample and the matrix, and then ejection of the molecules, and then they'll be analyzed. The fast atom bombardment, or FAB, uses xenon, so a noble gas over there to bombard it, and then the one that we'll look at a little bit more in detail is the MALDI, and that uses a laser to excite our matrix, which then transfers that excitement to the sample, and it gets ionized and thrown off of the matrix. Let's see. Oh, wait, yep. So here is the matrix. So they're putting the little samples on the little dot, that's their matrix.
watching the
shooting
sequel before.
And you can see they're shooting the laser at the samples, and the molecules are getting. Now they're flying into the mass spectrometer to be analyzed.
What? They got fragmented into different things. What's a CID cell? I don't know. I just know that chemical ionization
So
D
in the
something.
moldy, you have your sample that's actually absorbing the UV light. Like in our UV viz, talking about ionization. And actually we're looking at a different wavelength of UV light. So we're actually ionizing, so breaking bonds. And that excites the molecules and they get transferred into the vapor phase and sucked by the vacuum into the mass spectrometer. The nice thing about the MALDI or any of these desorption ionizations is that you can use the non-volatile samples. For your reactive materials. So this MALDI technique is used for very large molecular weight compounds like proteins and things like that. And let's go through the advantages and disadvantages. So here we can use a solid or a liquid sample. They can be high molecular weight. And it can be used with the MS technique, as I mentioned, for proteins and things like that. Gives you a lot more structural information. Because you might imagine that just having a single ion for a protein is not going to give you a lot of information. You know that your protein is 16,100 AMUs. That's not giving you a whole lot of information about its substructure. But if you can fragment it into pieces, you can then get chunks of it to know approximately where things are. And you can do additional techniques to get that information. And disadvantages, your matrix can cause side reactions. And your matrix background ions can be a problem as well. So if you're kicking out some of the matrix and it's getting charges, they're going to show up in your mass spec as well as the proton, or the sample you're looking at.
Is this a really expensive method?
Yes. It would be an expensive method as well. That's why they need fancy videos to sell it. If you're doing proteins and things like that, you have to do it and figure out the right method for it. But if you're just looking at small molecules, not so useful, because we have less expensive techniques that give us just as much information. Okay, we'll go over the last one, and then we'll talk about your writing and project information. So the last one is the electrospray mood ionization. And this video is electrospray, but it's not attached to mass spec.
pockets of substance. Electrospray starts with a liquid formulation, pushed through a capillary at a precise and constant flow. When an electric field is created by wiring the liquid to a high voltage, the meniscus rapidly turns into a stable cone, out of which a jet of liquid emerges and becomes a stable spray. This is the cone jet mode. Primary micrometric and highly charged droplets are formed in the jet. Due to electrostatic repulsion, they break into finer charged droplets, which themselves break into smaller and smaller ones, thus becoming nanometric.
Yes. Yeah, because the electrospray, the potential that you're putting on the sample as it's coming out, is causing the ionization. And so it's going to be ionizing your sample. Note that this is a sample in a solvent, so it could be in a liquid like water or some other organic solvent, and it's causing the molecules to get ionized, number one, and it's going to cause them to break up into really fine droplets. The really fine droplets, though, we can't analyze. We need them to be the individual ions. And in a mass spectrometer, you're going to have an evacuation chamber that comes after that, and it's going to evaporate off all the neutral solvents, and that's going to leave you with your ions as single ions. And you can see the droplets getting smaller and smaller as they're breaking apart. Remember that charges are going to repel each other, so if you have two molecules that are charged in a really little tiny droplet, the droplet's going to try and break apart rather than keep those as the water evaporates. Once all of the solvent has evaporated, they're going to be put onto the mass spectrometer to be detected. This is the way that most of the liquid chromatography is done with mass spec, because you got to get rid of that solvent that's coming off. It's also used for a lot of biomolecules. So advantages here, you don't have the matrix. So you don't have the background signals or side reactions. And it's commonly used for the LC mass spec. Because you need to get rid of that solvent as it's coming off. Sorry, I'm neglected to write down meters.
Expensive?
Yeah, expensive in some ways.
Do you ever have problems with not being able to get all the solvent on?
That's something you would have to fine tune with the parameters, yeah. So you need enough, a really high vacuum and enough airflow to be pulling that solvent off, and you may see that as a problem. An interesting thing with the electrospray ionization, remember how I keep telling you that the mass spec measures mass to charge ratios? Here's where it becomes relevant. So, mass to charge ratio. We've always assumed that our charge is 1. In electrospray ionization, that may not be the case, especially when you have large things like proteins that you're trying to put onto the system. You're going to get multiply charged ions. So multiply charged ions. So let's say you had one protein protein in one of these little droplets, but there were several positive charges. Proteins can be ionized in several places, and you may get a protein that has 4 hydrogens lost. So now you have your M minus however many hydrogens, and it would be a charge of negative N. Or, if we're in positive mode, you add some number of hydrogens and you get a positive N. This can give us mass to charge ratios of your molecular ion divided by 2, divided by 3, however many, whatever N equals, you're going to get different molecules or ions that you're detecting. And then, for example, if our mass was 10,000, you're going to see 5,000. If it was 10,000 divided by 3, 333. So you're going to see different ions, and you have to have a way to correlate those. And they have ways to do that if you're getting into it. But I can go over those. Okay, very briefly. So the spectroscopy project is going to be a presentation on one of the techniques that we're not covering in this semester. So they're not ones in the book, but they'll be ones that you'll seek out additional information. The techniques that we will talk about will be there, and you'll break up into groups of, I think I want to do groups of 3, so we don't have quite as many presentations we're trying to do. Now, there's several different pieces that you're going to need to include, so you're going to have to introduce this topic to the class, and it is going to be on the final exam for this information, so you need to do it in a good way so that everybody can understand it, and I can test you on it.
What's ho-ha-ha?
Ho-ha-ha. Homonuclear Holtzman Hans or something like that. Named it after themselves. Yeah. So, those of you not in writing intensive, you will be, well, no, let me see. Everybody's giving the class presentations together, but those of you in writing intensive are going to write an additional paper based on this material. One word of warning though, I know that someone that's writing a paper may do a lot of the research on their own. The presentation needs to include something that's not from the written paper, so I can see contributions from other people of the work. Okay? Here's how I'm going to do this. I'm going to create a blog on our Blackboard page, or a wiki, I think. And I'm going to put all these topics here with space for people to sign up. So you guys need to form groups of 3 and decide on one of these and sign up on the wiki, I think is what it is. And you can,
Under the discussion.
they're first come, first served in that way.
There's under the discussion.
There are I'll post all this, there's lots of instructions on what you need to include and formatting for the written report, and I'll post group